If we expand our thinking beyond just the PF interval, whereby P represents the point in time when the potential for failure exists, and F represents functional failure, we see that the longest time interval, typically, is between the point of installation, point I, and point P. This is known as the IP interval, and is likely the best opportunity to reduce or mitigate failure mode effects, as these tasks are intended to prevent point P from occurring, thus eliminating or at least prolonging the potential for failure.
If you had brought it in a little earlier, we probably could have caught that. It's going to run about $3,500 with parts and labor, and we don't have one in stock, so you're looking at least a week lead time on that. Whether it's your home, car, or equipment at work, ignoring small problems usually leads to larger ones.
Collection and exchange of reliability and maintenance data for equipment guides maintenance and reliability professionals through the formation of asset hierarchies. Hierarchy is defined as a series of ordered groupings of things within a system. In the case of reliability engineering, this refers to the physical equipment, machinery, and related structures within a facility that are used to process or support the processing of products. The hierarchy in a plant is important because it forms the backbone of any information management system in which data is stored and used as a part of running the business. These systems include, but are not limited to, accounting, production, maintenance, and stores.
Today we're going to talk a little bit about the scheduling side of the planning and scheduling process. Each one of these rocks represents a job. This is a little bit more of a large rock. May represent a job that has multiple crafts, maybe an electrician, mechanic working together. It also has multiple hours, so it's a bigger piece of our scheduling process. This is a smaller rock here, and this smaller rock may represent a job that just has 2 electricians, or maybe even only 1 electrician, and an hour or 2 of time. What I'm going to talk about is how we take those jobs and we sequence them into the schedule 4 weeks in advance.
Engineered asset strategies can be designed once we have a basic understanding of how each piece of equipment, or asset, fails. We tend to assume that assets fail primarily because of age and use. This is rarely the case. Here we have the 6 known failure probabilities, or curves. The predominant failures associated with all of our assets fall within one of these 6 shapes. Failure curves bathtub, wear out, and fatigue show how some assets experience a higher rate of failure when they reach a definitive end of life. There is a saying among pilots that only the takeoff is optional. Once in the air, you will be required to land one way or another. Pre-flight inspections are a key component of the process for determining if the aircraft is defect-free and able to both take off and land safely. Each aircraft should have a written checklist that identifies the components of the aircraft to be inspected in a logical order that enables completion in a single loop. The checklist is designed in such a way that even someone who is not a certified airplane mechanic can recognize a problem using basic sensory techniques. The principles of aircraft pre-flight inspections are easily applied to industrial equipment. Checklists can be developed for equipment that alerts the inspector to an abnormal condition. Basic care inspections are an effective way to supplement traditional PM inspection programs. Just ask any pilot. To see how all this works, let's start with vibration in your car due to a tire being out of balance. Assume the unbalanced mass is here at the 9 o'clock position. Let's draw a dotted line down to a point that will represent that position. The bottom side, or x-axis of the graph we are building, is time. As the tire rotates, the new positions will happen later in time. When the tire rotates 90 degrees, the unbalanced weight will be in the 12 o'clock position. Again, we draw a dotted line down to a point that represents this location. It will be further up and to the right because it is later in time. As the tire rotates, so the unbalanced mass is back at the starting point, the 90-degree markings are marked on the graph. Here we see a schematic of a set of rotating assets that are performing different functions in series in order to support the primary function of the air handling system. For example, the motor in this illustration is generating power, and the sheave and drive belts connecting the motor and fan drive shaft are transmitting power. Click the Start button when you're ready to play. When managing machinery dynamics within a conveying system, you must consider those mechanisms that impact friction. For example, if the load you want to convey increases, then so does the amount of friction between the sliding and conveying surfaces, and as a result you can't move the load as fast, or maybe even not at all. If the load weight decreases too much, then the conveying surface will simply slide under the load, and the load won't go anywhere.